and then set up share screen like I usually do, because there's an awful lot to review tonight, unless everybody remembers everything about time reversal. Let me see here. Let me share this. Plug in. Yeah, thank you. So every 3 or 4 times it requires a plug-in. Fortunately, it goes. Okay, good. Let's see here now. All right, let's get this here. Okay, there we go. So do these little reviews I do before the real class starts, are they helpful to you, or what do you think?
I find them valuable personally, but
Yeah, I think so.
Yeah, if I just dive right into where I was, it's kind of hard, probably. Yeah, okay, so I've got a lot to review, so I'm going to get started on it. So this is a review of what we've done with time reversal. So so we have the basic question is that if you have a solution of the Schrodinger equation and it's time-dependent solution, and then you just define a time reverse solution by taking t goes to minus t. That just means running the movie backwards if you got a movie of the wave function. The question is, does that work as a solution? Is that also a solution to the Schrodinger equation? And the answer is no. That doesn't work. You have a buzzer sound, bad sound that happens for that. Which you see if you take the case of a charged particle in an electrostatic field, which is a simple example. What you find is you have to complex conjugate the wave function, and then it does work, at least for that example. So what this shows is that in addition to switching t to minus t, you also need to apply an additional operation, which in general we'll call the time reversal operator theta, or in Ket language it looks like this, is the time reverse solution psi r of t. The r here means reversed, is the psi running backwards, but then additionally this operator acting on it. The time reversal operator by itself does not involve time. I mean, complex conjugation just maps wave functions into wave functions. It doesn't do anything to the time parameterization. So it's a Hilbert space operator, and this is what it is for this simple case. So in general, we're going to expect then that the time reversal solution psi r of t is some time reversal operator applied to psi played backwards. And we call theta the time reversal operator. It doesn't involve time. If you set t equals to 0 in this equation, what you see is that the initial conditions for the reverse motion are the time reversal operator acting on the initial conditions for the unreversed motion, the original motion. Actually, you'd have something like that even in classical mechanics, is that if you want to run the movie backwards, the movie running backwards is supposed to be a solution of the equations of motion. The initial conditions are going to be different because the velocity switches on time reversing the initial conditions. So there's, even in classical mechanics, there's got to be some operator in addition to flipping t goes to minus t. All right. Anyway, what we expect then, based on these initial condition relations, is that the time reversal operator ought to take x into x and p into minus p, because that's what you need to do to reverse motions and potential problems. And if it does that, then since x cross p is orbital angular momentum, that should go into minus itself. And then given that, we argue that all angular momenta ought to behave the same under time reversal. So we require that theta should conjugate j and take it into minus j. So this is basically a set of postulates that the time reversal operator ought to satisfy. Okay, so what we find though, by looking at those postulates, is they cannot be satisfied by any linear operator, unitary or otherwise, can't be satisfied. You need to have an antilinear operator. So this takes us into a big digression on the properties of antilinear operators. And they have 3 properties that differ from those of linear operators, which I've listed here. One is that they don't commute with constants, which are regarded as multiplicative constants, but rather when you pull the A through one of them, an antilinear operator through one of them, you have to complex conjugate the constant. The second rule says is that in the case of antilinear operators, it does matter which direction it acts in a matrix element. So you have to introduce parentheses to show which direction it acts. Also, if you reverse the direction in which it acts, you have to complex conjugate the matrix element. That's what we've got here. So just reordered the parentheses there, but we had put a star on it. The third rule says that if you take any expression involving any collection of operators, linear or antilinear, whatever, bras, cats, whatever you want, and you want Hermitian conjugate it, what you do is you read it backwards and conjugate all the ingredients as you move along. That's the usual rule, as a matter of fact. But what's different here is that you also have parentheses, and so the new rule is that you have to reverse the parentheses as well. And right here's an example of what you do with a quote unquote matrix element. A dagger gets converted into A like this. If you like, this formula can be taken as a definition of A dagger for a antilinear operator. All right, so the next we turn to what I call the LK decomposition. The idea is you've got some given antilinear operator and you factor it into a product of a linear operator times another antilinear operator, which we'll call K, and K is chosen to be simple, and the L then takes care of all the rest, the linear part. So that's the idea of this decomposition. The type of operators K, the simple ones that we encounter, are usually of the following type. We let Q be some complete set of commuting observables with eigenstates n like this. So this is the eigenvalue eigenvector problem here. Then K, with reference to that complete set of commuting observables, is defined by the fact that K sub Q, that first of all, it's antilinear, and that secondly, it takes the basis states into themselves with no multiplicative factor or anything like that, just reproduces them. So this is what the effect of such a KQ does on a wave function. If we take a wave function and expand it in the given basis with coefficient C sub n, then applying K sub Q, the K sub Q complex conjugates the coefficients because it's antilinear, and it doesn't do anything to the ends. So this is what you get for KQ acting on psi. So what you can see is that KQ is an operator, an antilinear operator, which complex conjugates the wave function in the Q representation, because that's what these coefficients are. That's the wave function in the Q representation. All right, so that takes me up then to what I wanted to say in review of antilinear operators. And I used up a little more time than I wanted to, but that's okay. So I want to continue with that thought then, with developing some of the properties of the KQ operators that are so defined. One of them is, it turns out the KQ is they're not only antilinear, they're actually anti-unitary. So KQ is equal to KQ dagger, and in fact, it's also equal to KQ inverse. And this implies, amongst other things, that KQ squared is just equal to 1. The fact that KQ squared is equal to 1 is kind of obvious, because KQ leaves the eigenkets, the basis kets, alone. If you apply it again, it leaves the basis kets alone again. So now you've got an operator which is now a linear operator, which maps the basis kets into themselves. Well, that operator can only be equal to 1. If it's an antilinear operator that maps the basis kets into itself, not only is it not equal to 1, but it doesn't even make any sense to write it equal to 1, because you're equating a linear with an antilinear. 1 is a linear operator. Well, anyways, K squared is linear. All right, so K squared equals 1 is pretty easy to see. But let's get some of these others here. Let's take a look at KQ dagger. So let's take KQ dagger and let it act on a basis ket n. And we'll fix this up by inserting a resolution of the identity. Let me call it MM here, outer product, like this. And then we have the KQ dagger n, KQ subscript dagger superscript n like that, which is where we started. But I better put parentheses around it, because that KQ acts to the right. Now then, this matrix element, what I'm going to do is read it backwards, and then I have to complex conjugate it according to the rule. So I get the parentheses, I get bra in now, I get KQ without the dagger, I get the closed parentheses, and then I get an M like this, but I had to complex conjugate it, because that's what I'm doing, is complex conjugating this matrix element, is reading it backwards. There should have been no dagger on that, because it got undaggered in reversing everything. I'm going to let this KQ act to the right. I want to change the direction in which this KQ acts. According to parentheses, it's acting to the left. I want to move it to the right. Well, I can do that if I change the parentheses, and according to the rules, I then need to conjugate what I have. That just removes the other conjugate that's already there. So I get this. Now KQ acting on M is just M, so I get the scalar product of NM, which is Kronecker delta NM, like so. So this is an example of manipulations you can do with antilinear operators. And the result is that this whole matrix element here is just a Kronecker delta NM, and therefore this whole sum just becomes equal to N all over again. So we see the KQ dagger acting on N just gives us N, and that means that KQ dagger is equal to KQ, because that's what KQ itself did. They're the same operator. So these two are equal, and given the fact that KQ squared is equal to 1, it means KQ inverse is the same. So this KQ then is an anti-unitary. It's not just anti-linear, it's anti-unitary. And also its square is equal to 1. All right. Now, that's some facts about these K operators, which are used in the KQ decomposition. To change the subject slightly, we've said a lot of things about this time reversal operator, but we haven't actually said what it is for specific systems. So let's work on that. Let's start with initially with the cases where we have only spatial degrees of freedom, which is a way of saying that we've got a particle. Let's say it's one particle. So we just got wave function psi of x. And we'd like to know what theta is on this system. Well, the requirements that we've imposed on theta is that it be anti-unitary, and that it should take x into itself, but it should take momentum p into minus itself. And so because we can apply an LK decomposition, let's do it. Let's write theta is equal to L times K, and for K, let's do the K is a complex conjugation operator. Let's do it in the X representation. So this is the operator that complex conjugates the usual wave function. I'll do this in a one-dimensional notation here. Let's see what happens if we do KX X. Let's put a hat on for an operator, KX dagger. Let's check this out, except I'll just use the K part and not the L part and see what happens. So let's take KX and conjugate the X operator. We can do this by looking at wave functions. If I have psi of X and I apply first of all the KX dagger to it, well, KX dagger is the same as KX by what we saw up there. So that just complex conjugates it. So that turns into psi of X star. And now I'm going to apply the X hat operator here. X hat's the operator. This just gives me X times psi of X star, because it's just multiplication by X. And then I apply the K, which is the third factor here. The KX is the third factor. And this complex conjugates it again and turns into X psi of X. So what we see is that the product of these three operators is equivalent to just multiplying by X, which is X hat itself. All right, now what about momentum? Let's do KX P hat, KX dagger. So again, we have psi of X under the KX dagger goes into psi star of X. Under the momentum P hat, this goes into IH bar, minus IH bar, excuse me, ddx of psi star of X. And now under the KX, we complex conjugate it again, and it turns into plus IH bar ddx of psi of X. And you can see that that's minus the momentum operator acting on psi. So K conjugating P gives us minus P. And so what you can see is that the KX conjugation, complex conjugation operator by itself satisfies these two requirements that we have for what time reversal should do in a simple system like this, where we have only spatial degrees of freedom. And therefore we can take the time reversal operator for such systems to be equal to K, and I'll put this X vector now for three-dimensional problem in the X representation. This agrees with what we did earlier when we found you needed to complex conjugate the wave function to get the time reverse solution, and that's what this is showing too. This is following its required properties on its action on the initial conditions. All right, so that's the case of spatial only. Let's now look at the case of spin only degrees of freedom. I'll take this one step at a time. For spin only, of course, the basis states are let's just call them M like this, where M runs from minus S up to plus S. And this is the S sub Z representation. Of course, there's S squared in there too, but S squared is kind of a constant. What do we require of the time reversal operator in this case? Well, we don't have any X and P, but we have a spin operator, which is the angular momentum for the system. And we decided that time reversal needs to change the sign of angular momentum. So let's take this theta. We know we can write it as an LK decomposition. And for the K, let's choose it as complex conjugation in the S sub Z representation. So what does that mean? So let's start by checking out what K sub S sub Z does to the three components of spin, Sx, Sy, Se, when we conjugate. K sub S sub Z dagger. What does that do? Well, the answer is pretty easy to see because the matrices for Sx and Sz in the usual basis are real, whereas the matrix for Sy is purely imaginary. So this is going to leave the Sx and Sz alone, but change the sign of Sy. And so the complex conjugation alone does not give us the conjugation relations we need for a spin system because it only flips the sign of S sub Y. Therefore, we're going to need to have some linear operator that takes care of the rest of that in order to get the desired time reversal. So now we seek a linear operator that leaves Sy alone, but flips the signs of Sx and S sub Z. Well, that linear operator is easy to see if we draw a picture here, X, Y, and Z here, coordinates, like so. And you can see that if I rotate about the y-axis by an angle of pi, it'll change the sign of both the x and z components of a vector, but it'll leave the y components alone. So let's take this thing here and let's conjugate it by a rotation about the y-axis by an angle pi of this Sx minus Sy and S sub Z here, like this, and then U of y hat comma pi dagger. For this, we can use the adjoint formula, and it amounts to just doing a classical rotation of that vector. And as I just explained, that's going to give us what we want, minus x, minus Sy, and minus Sz. And so what we see is we can take the time reversal operator to be equal to e to the minus I pi S sub y over h bar. That's just this rotation. That's all that is right there, times the complex conjugation in the S sub Z basis. And this is the time reversal operator for spin only, for a system that has only spin. Okay. Now, what about time reversal operator for a system that has both space and spin? Well, in that case, it's easy to do. We just take the earlier result where we complex conjugated an x, and we sort of just combine it with this one. So what we'll get is that we get a spin rotation, either minus I pi Sy over h bar. And we now take the complex conjugation in the combined x and S sub Z representation, like that. And so this is for the system of a spinning particle where we have spatial and spin, spatial plus spin, time reversal operator. Okay. Now, let's do an example. So that's the conclusion. Let's do an example here and see what that looks like. Let's take the example of an electron, which of course has a spin 1/2. So the electron wave function is a two-component spinner. I can write it psi of x as a two-component thing with a psi plus component of x and a psi minus component, where the plus and minus, of course, refers to the eigenvalues of S sub Z, which is plus and minus 1/2. So this is in the x S sub Z representation. That's fairly standard notation or representation to use for particles with spin. And so what K is going to do here is to complex conjugate that. But we also have the spinner rotation. Now the the S sub y, the y component of spin for an electron spin 1/2 particle is h bar over 2 times sigma y. And so the rotation operator that we have here becomes e to the minus I pi over 2 times sigma y. And that's equal to, if you work it out, it's 0 minus 1, 1, 0. In fact, it's one of these reduced matrix elements, the lowercase d matrix elements with an angle of pi. That's what this is. This is d 1/2 of pi. That's what that matrix is. So to transform this side then under time reversal, I want to transform it under time reversal theta. I need to first multiply by this matrix and then take the complex conjugate. So what I'm going to get is I get minus psi minus of x in the upper slot, and then I get plus psi plus of x in the lower slot. I'm just multiplying by 0 minus 1, 1, 0, this matrix times that column. But then I also need to complex conjugate it. So this is what time reversal does to an electron wave function, a two-component wave function. And you see it's more complicated than what we have for a scalar particle without spin, where we just took the complex conjugate. All right, so that's the definition of time reversal then in these two cases. Spatial and spin, 3 cases, including the case of spatial plus spin. I'll talk about multi-particle systems in a little while, but that's enough for now for our definition of time reversal operators. So we've got they're partly guesses here, but these are useful definitions of time reversal operators. Now let's go back to what we started with, that the time reverse motion psi r of t ought to be equal to our time reversal operator, if we defined it right, times the original motion evaluated at minus t, like so. Let's work on this and see what we get out of this equation. For the original motion evaluated at time minus t, what we can do is take the unitary time evolution operator evaluated at minus t and apply it to the initial conditions, psi of 0. And that's the same thing as copying the theta. The u of minus t is equal to e to the plus I th over h bar. Usually be minus I, but I got a minus t or changes it to a plus sign. And then I'm going to insert a theta dagger theta here, which gives us 1 because it's anti-unitary. And then I've got the psi of 0, which I just copy again. And the theta acting on psi of 0 gives us psi reversed of 0, because that's what theta does, is it maps initial conditions into the reversed initial conditions. And as far as the first 3 factors are concerned, we can bring the theta theta dagger conjugation up into the exponent. So this becomes the exponential of theta on the left, and then I h t over h bar in the middle, and then theta dagger on the right, like so. Now, when we bring the theta through the I, it changes to minus I because it's antilinear. Let's define h prime to be equal to theta times h times theta dagger, so that h dagger, so that h prime, we can call this the time reversed Hamiltonian. That's what's appearing up here. So this thing then becomes equal to e to the minus I h prime t over h bar. So putting this all together, what we get is the time reversed motion, the one that we're going to see in the movie, is equal to e to the minus I h prime t over h bar times psi reversed of 0. And what we see from this is that the movie, running the movie backwards, gives us an actual evolution of the Schrodinger equation in the time reversed Hamiltonian, h prime. Now, if h prime should equal to h, which means that the original Hamiltonian commutes with time reversal, then the time reverse motion is actually a solution as well, or is a solution in the original Hamiltonian. That's normally what we think about when we run movies backwards. When I ask, is it an allowable motion? Even classically, sometimes it is and sometimes it isn't. But what we see now is that it will be allowed motion if the Hamiltonian is invariant under this time reversal operator. Okay. Now, okay, so this now raises the question then of, well, is the Hamiltonian invariant under time reversal? And the answer is it depends on the Hamiltonian. So let's take some examples and see. It's kind of like parity in that respect. Let's take, for example, a simple kinetic plus potential problem, p squared over 2m plus a potential which shall allow depend on x, like so. If I take this and conjugate it by time reversal theta theta dagger, what theta and theta dagger are going to do to the vector is change its sign, because it's odd under time reversal, but since it's p squared, it won't affect the kinetic energy. Time reversal doesn't change the position, however, so the potential v of x is the same. So this is an example of a Hamiltonian that's actually invariant under time reversal. This is equal to, if I put the h in here, this becomes equal to h. It's equal to itself. So this is a case where the time reverse motion is, in fact, a solution of the original equation. On the other hand, the theta, as I've explained, is just complex conjugation. So that takes us back to our earlier conclusion, a special case of just potential motion. What if we try it with a particle in a magnetic field? This could be an electrostatic field. Let's try it with a particle in a magnetic field. In that case, we've got P minus Q over CA, the vector potential, which is a function of X. That whole thing gets squared over 2M. And then we've got plus the potential V of X, like so. And now you can see, so here's your Hamiltonian. And now you can see that if you conjugate this under time reversal, theta theta dagger on the two sides, what's going to happen? Potential energy as before won't change. However, the momentum will change sign. It'll go to a minus p, like that. It turns into, well, it's a plus p now, but when I conjugate it, it'll turn into a minus p. And so the kinetic energy in the a of x won't change because it's a function of x. So the kinetic energy operator changes. And this is an example in which the time reversed Hamiltonian is not the same as the original one. So motion of a charged particle in an external magnetic field is an example, in fact, it's the main example that everybody thinks about of a system which is not invariant under time reversal. However, you may notice if I did change that p to a minus p, that I'd get the same results as before if I also change the sign on the A. So in effect, the time reversed Hamiltonian is, in the presence of an external field, is the Hamiltonian in which the magnetic field has been reversed. If you do that, then running the movie backwards and applying theta actually gives you a motion in the time reversed Hamiltonian. So external magnetic fields break time reversal. However, it turns out that if the magnetic field is produced internally, then it does not break time reversal. An example of this is the spin-orbit coupling, which appears in the relativistic corrections in an atom. This is a term in the Hamiltonian that goes proportional to L dot S. The spin-orbit coupling physically is a magnetic effect that involves the interaction of the spin of the electron with a magnetic field that it sees due to the nucleus in its own frame, which is a moving frame. And as I say, it's a magnetic effect, but it's internally generated. Now, if I conjugate this with time reversal, look what happens. All angular momentum vectors change sign under time reversal, so there's two changes in sign, and the result is this is left invariant. So this is an example of an internally generated magnetic effect, which is invariant under time reversal. The reason that this works is because all electromagnetic effects, in fact, are invariant under time reversal, just as they're invariant under parity. So we can extend this now to more complicated electromagnetic effects, including emission and absorption of radiation, retardation, and all the rest of it. Full electromagnetism is invariant under time reversal. So the next question then is, are there any isolated systems which are not invariant under time reversal? Well, to answer this question, I want to take you back to the history of a parity violation, which I covered briefly in a previous lecture, not so long ago. And I explained how in the mid-1950s, contrary to the belief of everyone up to that point, it was discovered rather quickly that the weak interactions violate parity. They do so in a rather maximal way, as a matter of fact. Now, this saga leads into the subject of the CPT theorem, which I want to tell you about now. CP and T refer to three symmetries. The first is charge conjugation, second is parity, and third is time reversal. So we've been talking about the latter two in the last couple of lectures. Charge conjugation can't be understood very well in non-relativistic quantum mechanics. It really becomes realized in field theory, relativistic field theory. But the basic idea of charge conjugation is that it replaces every particle but with its antiparticle. Positrons go into electrons and vice versa. Now, it's believed in relativistic quantum field theory that all physical fields, quantum fields, are symmetric under the product CPT. That this is an exact symmetry of the system, and the reasons it have to do with Lorentz invariance and the fact that, or the belief that signals can't propagate faster than the speed of light. The principles upon which the CPT theorem are built are pretty firmly established, and most physicists believe that they're correct. And so there's a wide belief, a strong belief, is that CPT invariance really is a rigorous invariance, a symmetry of nature. However, as I just explained, in the mid-50s, it was discovered that parity is violated by the weak interactions. In those experiments that violate parity, it was observed quite quickly at the same time, really, that although parity was violated, that CP, the product of C times P, was not violated. If you complex charge conjugate, you get back to the original system. So there was a certain period of time in which it was believed that at least CP would be a good symmetry. And of course, if that were true, and you believe the CPT theorem, then time reversal would also be a good symmetry. However, within about 7 years, it was discovered experimentally by Fitch and Cronin, they got the Nobel Prize for this, that there's CP violation in the decay of the K mesons. And so CP symmetry went out the window. And so quickly, within a period of 10 years, it was discovered that not only is parity violated, but also CP is violated, which implies violation of time reversal if you believe the CPT theorem. Okay, so this is just the state of things now. It's well known that we have both time parity violation and CP violation. Actually, we also have time reversal violation. So this is an important basic fact about physics that led to Nobel Prizes at the time of the discovery, because everyone understood how important it was. To give you some idea of how this affects current physical thinking, the fact of CP violation leads to one of the current beliefs on how it is that, or explanations for why the universe has an asymmetry between matter and antimatter. The basic idea is that when the Big Bang happened, is that both matter and antimatter were created in nearly equal amounts. The small discrepancy between the two being due to CP violation in the early universe, in the processes that created the particles. Then, as the universe expanded and cooled off somewhat, the matter and antimatter mostly combined together and annihilated. And the result is what was left behind is a small residue of which turns out to be matter. And that, of course, is what the visible universe we have today, including ourselves, is made out of. So this gives you an idea of some of the fundamental questions that time reversal invariance plays a role in. All right. Anyway, so that's some digression then on CPT and CP violation and time reversal and so on. All right. Now, so far what I've explained is what time reversal does for the time evolution of systems. Now I want to say something what it does about energy eigenstates. Actually, before I do that, I need to make some preface some remarks. Let's suppose we have a Hamiltonian which is invariant under time reversal, so that theta h theta dagger is equal to h. And let's suppose I have an eigenstate of an energy eigenstate of h, which I'll call psi. If I consider time reversal acting on psi, and I let h act on that, because h commutes with theta, I can bring the theta out, and I get theta times h psi. The h psi, of course, brings out e, but e is a real number, so I can bring theta through that, and I get e times theta psi. And so we get a simple result, which is worth saying in words, is that there's various ways to say it, is that if you take an energy eigenstate and you apply a time reversal to it, for a time reversal invariant Hamiltonian, you will always get another energy eigenstate of the same energy. Now that new energy eigenstate might be linearly dependent on the old one, and if so, you haven't found anything new. But if it is linearly independent, then you see you've got a degeneracy, you've got an extra state of the same energy. All right, now I'll get to the questions of degeneracies in a minute, but there's another general fact I want to talk about now, which is that we should consider the operation of theta square, the square of the time reversal operator. Well, let's look at theta itself first. I gave it to you earlier for a single particle. If we have a multi-particle system, we just multiply those operators together. So let's say we have a multi-particle system, then I have e to the minus I sy for particle 1 times pi over h bar for the rotation. Then I have kx s sub z for particle 1. And then I just repeat these factors all the way out to the nth particle like this. This will give me the time reversal operator for a collection of particles in various spins. Now these factors, these these complex conjugations and these spin rotations commute with each other because the spin rotations are represented by real matrices, because they're in the rotations about the y-axis. So we can rearrange the order of them. Now then, if I do that, then if I put all the spins together, then I get an exponent with sy1 plus sy2 plus dot dot dot, which is of course the total sy of the system.
Sorry, just a question.
Yes,
if I can.
Yes.
Why would you not change the sign of the I and the exponent when you move the commutations past the k matrices or k operators past them?
You do, but you see the matrix of sy is also purely imaginary, so it changes sign too.
Oh yes. Okay. Yeah.
Or to put it another way, this rotation operator, this rotation matrix is purely real. In fact, it's an example of those lowercase d matrices, which Wigner designed them to be real. So they commute with these k's. All right, so what appears in the exponent then of the spin part is just the total spin. So the theta then is equal to e to the minus I sy, which now sy refers to the y component of total spin times pi over h bar. And then a product of all the complex conjugation operators, and I'll just call this a grand total k, I'll just call it k like this. All right, so this is what we get. And this first factor, of course, could also be written in our notation that we've used before. Let me write as u sub spin of y hat comma pi. It means the same thing. That's what that is. All right. Now, as I said, it's of interest to compute the operator theta squared, the square of time reversal. If we do this, what we get is u spin of y hat comma 2 pi, because two of them get doubles the angle. And then we get the square of the k. And I've rearranged them, but as I explained, you can do that, rearranging, because they commute. Now, k squared is applying complex conjugation twice, so that's just the identity operator, and that goes away. So we just get the spin rotation by an angle of 2 pi. Now, what that is depends on whether the total spin of the system is integer or half integer. If the system is an integer, then rotation by 2 pi is just the identity, so the answer is +1. But if the system is half integer spin, and this is the spin I'm talking about, then the rotation by 2 pi is -1. So what we have is that theta squared is up here. Let me say this is theta squared is equal to that. Theta squared is either plus or -1, depending on whether you have a total spin that's an integer or a total that's a half integer. All right, so let's take these cases and see what this implies for energy eigenstates. Let's take case 1 for integer spin. Let's suppose we have a non-degenerate energy eigenstate. That's the simplest case to take. Non-degenerate energy eigenstate. Let's say h psi is equal to E psi. Now, as I just explained, theta acting on psi is an eigenstate of the same eigenvalue. And if it's non-degenerate, then it must be proportional to the one we started with. There must be some constant c such that theta psi is equal to c psi. It implies this. Now, if I square both sides, an antilinear operator preserves it takes the scalar products into their complex conjugates. So squaring theta psi is the same thing as squaring psi and taking its complex conjugate. The psi squared is 1, so the left-hand side, if I square it, just gives me 1. And the right-hand side gives me the absolute value c squared. So this shows you that c is a phase factor. Let's call it e to the I alpha. So let's write the equation again. The theta acting on psi is equal to e to the I alpha times psi. All right. Now, let's do this. Let's let it define a new state phi to be equal to half this angle, e to the I alpha over 2 times psi. Let's do that. And then let's see what time reversal theta does to our new state phi. Well, when I bring theta through that phase factor, it changes, complex conjugates it to e to the minus I alpha over 2. When I let theta act on psi, it brings out e to the I alpha and reproduces psi again. And you can see that the phases combine together to give you e to the plus I alpha over 2 times psi, which is the same thing as phi. So what we've got then is the state phi, which is the same as the original state, except the phase factor has been split off, is a new state which is invariant under time reversal. If you wanted to, you could say that it's an eigenstate of time reversal. People don't usually use that language with antilinear operators, but that's at least the idea. It's invariant under time reversal that theta acts on phi and reproduces it. So this is a proof then that for the integer case, integer spin, that non-degenerate energy eigenvalues you can always choose a phase factor for them, the phase convention for them, so that they're also invariant under time reversal. Now, if we apply this to a kinetic plus potential system, then it means that we can choose non-degenerate energy eigenstates so that the wave function is real, because time reversal is just complex conjugation. Now, that's a fairly trivial conclusion because the Schrodinger equation for kinetic plus potential problems is a real equation. So no wonder the wave functions can be chosen to be real. It's no big deal. However, this also applies if you include spin-dependent terms, for example, fine structure. Then it becomes much less trivial. You have wave functions which are now spinors, and there's these spin rotation matrices and so on. Anyway, it's still possible to make non-degenerate energy eigenfunctions into invariant under time reversal. This is oftentimes a useful thing to do. All right. Now, situation is actually more interesting in the case of half integers. Again, let's assume that we have a non-degenerate energy eigenstate, so H psi is equal to E psi, like that. Then we know that theta acting on psi is an energy eigenstate of the same eigenvalue. Now then, let's see, what did I want to do here? And in fact, we know that this must be equal to e to the I alpha times psi, because we worked that out a minute ago. All right, now let's, this for some phase alpha. Now let's apply theta a second time. On the left-hand side, we get theta squared acting on psi. On the right-hand side, the theta pulling through the e to the I alpha gives us e to the minus I alpha, with theta adjacent to psi, but theta and psi is e to the plus I alpha times psi. So the right-hand side just becomes equal to psi. But if you have half integer spin, theta squared is equal to -1, so that's equal to minus psi. And so what we conclude is that psi, if you have a non-degenerate energy eigenstate, then that psi is equal to 0 for half integer spin for Hamiltonians that commute with time reversal. Well, what that means is that there are no non-degenerate energy eigenstates. This is proof by contradiction that in the case of half integer spin with a time reversal invariant Hamiltonian, that all energy eigenstates are at least twofold degenerate. This is called Cramer's degeneracy. And as I say, to repeat it, degeneracy, it applies for time reversal invariant Hamiltonians for systems with half integer spin. Now, you actually saw an example of this on last week's homework problem, which was that electric dipole moment operator of a nucleus in an external electric field. Remember, there was it had spin 3 halves, so there's a 4-dimensional Hilbert space. But the physics of it was electrostatics. And electrostatics, remember, is invariant under time reversal. So what was happening there is you found that the 4-dimensional Hilbert space actually broke up into 2 subspaces that decoupled from one another. And then in fact, the energy eigenvalues, we had 2 pairs of degenerate eigenvalues. Well, that's an example of Cramer's degeneracy. You see, the degeneracy comes in multiples of 2. Actually, all I've proved here in this little proof I just went through was that you can't have a degeneracy of 1, but a more careful analysis will show that the degeneracy is always in even number, whatever it is. In that problem, you had 2 levels, each of which was twofold degenerate. And that's an example of time reversal invariance. By the way, the degeneracy would involve mapping m into minus m, which is taking the z component of angular momentum or spin into minus itself. And that's a reflection of the fact that time reversal changes the sign of the spin. So there was an example of Cramer's degeneracy. All right, that's all I want to say about time reversal. Are there any questions about that before I move on to another topic? All right, it's a
Sorry, can I ask a question?
yes.
Oh, I might have missed this. Where was the assumption that this was a non-degenerate eigenfunction?
Well, in both the integer and the half integer cases, I assumed that it was a non-degenerate eigenfunction just to see what would happen. So in the integer case, what you find is that you can always choose a phase factor to make that eigenfunction invariant under time reversal, wherever it is wherever it is there. It's here. Theta phi is equal to phi. In the case of total half integer spin, again, I just start out by assuming. Let's assume we have a non-degenerate energy eigenstate. What you find in that case is a contradiction. In other words, there are no non-degenerate energy eigenstates. All energy eigenstates are degenerate, and that's called Cramer's degeneracy. Now, a more sophisticated analysis would show you that in systems with time reversal invariance with a half integer spin, that all energy eigenstates have an even fold degeneracy. It's not just greater than 1, but in fact, it's always an even number. Does that explain it?
I think I'm just having trouble seeing where the difference between the integer and the half integer cases. So in the integer case, we defined a new phi at pulling e to the I alpha over 2 psi. Where did that come from?
Change the phase convention of that state. And by doing so, we end up with a new state, which is invariant under time reversal.
So why can't we do that for the half integer case?
Because in the half integer case, you find that if you assume that you have a non-degenerate energy eigenstate, you end up with a contradiction. You end up psi is equal to minus psi, therefore psi is 0. There are no non-degenerate
Right.
energy eigenstates. This is proof by contradiction.
Okay.
Okay. So in the case, actually, there's a whole world here of half integer spin and time reversal. It turns out the wave function and the Hamiltonians can be expressed in terms of quaternions. There's a whole universe out there of this particular case. It's quite important in practice, actually. This is just touching the most basic fact is that all energy eigenstates are degenerate. I mean, we might have started out by assuming we had a non-degenerate energy eigenstate just out of curiosity, just to see what would happen. But if you do that, you find that you get a contradiction. Unlike the case of integer spin, where it's okay, it works out fine in that case.
Why do we not get the contradiction for integer spin though? Because we have the same universal psi equals e to the I alpha psi.
Yeah, but the thing is theta squared equals +1 in the case of integer spin. Theta squared.
Oh, and not oh, okay, there. Okay, I see. Thank you.
Oh, okay,
Yes.
that makes sense.
It's related to this fact. You see the fact that these spin rotations by 360 degrees are a -1. Give you a -1 factor if you have a half integer spin. Okay.
Got it. Thank you.
All right, that's Cramer's degeneracy. It's an interesting business, actually. My research lately has been involving a lot of time reversal symmetry. All right, so I'd like to move on to a new topic now, which is perturbation theory. Let's get a start on that. I think you know what the basic story about perturbation theory is from the undergraduate course. To be more explicit, I want to talk about bound state perturbation theory. The systems, if you want to talk about realistic systems, they have a continuous spectrum as well as a bound state spectrum. But the bound state perturbation theory works with the bound states only. So let's do that. Let's write the Hamiltonian as H0 plus lambda H1. So that H1 is the perturbation and lambda is a parameter that we allow to vary between 0 and 1 in order to, was my voice lost there for a minute? I noticed that the picture was lost for a minute.
No, it was fine for me.
Okay, so sometimes the picture gets broken up, but not my voice. So lambda is a parameter that interpolates between the unperturbed system and the full system with a fully switched on perturbation. I think this is you understand how this works. We assume that H0 is solvable and that we've solved it. So let's talk about its energy eigenstates and eigenvalues. Let's call them K alpha for the eigenstates. They have an eigenvalue I'll call epsilon sub K. And the alpha index here is an index that's used to resolve degeneracies. We allow these to be degenerate eigenstates like that, and epsilon sub K then is the eigenvalue. Allow me to make a picture here. Let's make an energy axis here like this. And let's talk about the energies of H0. Can you see this down there? And so I'll put some energy levels in here. Who knows what they look like? Some might be close together. It might be one like that. So all of these are these various epsilon sub Ks that we have here, energy values. Let's pick one of them. Let's call it epsilon sub N, one particular unperturbed energy level, which I'll label by N, and we're going to study the perturbations on that level, which may be degenerate. So when I turn on the perturbation H0 plus H1, what happens to epsilon N in general is that it will split. If it's a degenerate, it'll split, and you get multiple levels like this that go off on various trajectories. Let's call the energy of one of them capital E. This is the exact energy of the fully switched on system like this. And let's call the corresponding wave function psi, or state vector psi. So this is the exact eigenstate of the system. So in other words, psi is defined by the equation that H0 plus lambda H1 acting on psi is equal to E psi. All right, now you may notice I left the lambda in here. I did that because it's sometimes useful to think of both the exact energy E and the state psi as functions of lambda. If you do that as you let lambda go to 0, then E approaches the epsilon sub N, which is the unperturbed eigenvalue over here. And as far as psi, what does it approach? What does it approach? Well, if the unperturbed eigenstate is degenerate, then it's multidimensional. So if I track psi here, scaling lambda back down to 0, what I'm going to end up with is a specific vector lying inside the degenerate eigenspace. And we'll see, depending how much time we have tonight, we'll see maybe tonight how it is that we know what that vector is inside that eigenspace. There's in the case that the non-degenerate, in the case that the unperturbed eigenspace is degenerate, there's going to be a question of where the psi ends up when we turn the perturbation down to 0. All right, so let me put it here. Let's just say that there's a question mark about this, but it'll definitely be inside the unperturbed eigenspace. All right. It helps to have a little bit of Hilbert space geometry and visualizing some of the algebra we're doing in perturbation theory. So let me introduce what I'll call script H sub n is the unperturbed eigenspace. This is the span of the basis vectors in alpha like this, the unperturbed eigenstates like this for alpha equals 1, 2, and so on. So that's the unperturbed eigenspace. Let me draw the Hilbert space in a schematic manner like this. It's a vector space, of course. Let's make this axis the Hn, that's the unperturbed eigenspace, and let's make this axis the orthogonal space, which I'll call Hn perp, like so. So the unperturbed energy eigenvectors lie inside Hn, like sort of on this Hn axis here. Now, if we're doing perturbation theory, the exact eigenvector presumably does not differ very much from the unperturbed eigenvector. So in a diagram like this, it's mostly going to have components along the Hn direction, but it's also going to have something orthogonal to it as well. So if I call psi then the exact eigenvector like this, then we can think of decomposing it into its components perpendicular and parallel to the unperturbed eigenspace Hn. You know, in many applications, Hn is going to be finite dimensional. It could even be just one dimensional if it was non-degenerate, whereas the Hn perp is everything else, so that's going to be infinite dimensional. But there's also cases where Hn could be infinitely dimensional too, so you have to keep that in mind. All right, in any case, it's convenient in talking about these projections here under these two different spaces to introduce projection operators. Let me introduce the projection operator P, which projects onto Hn. This is a sum on alpha of the outer product n alpha with itself. And then the complementary projector I'll call Q, which projects onto the orthogonal space. This is a sum on all k not equal to n and sum on alpha of k alpha outer product with itself. So these projectors have the properties that, first of all, p squared is equal to p and q squared equals q. All projectors satisfy those relations. Also, pq equals qp equals 0. That means they project onto orthogonal spaces. And also the fact that p plus q is equal to 1, because if you add them up, you get a resolution of the identity. All right. Now then, so those are our projection operators. So this long vector here, which is in the direction Hn, is the same thing as p psi. And this short correction orthogonal to it is q psi. Now it's useful to think of p psi as being the large component. In fact, if you're doing perturbation theory, it's going to be the large component because, as I just said, psi is presumably close to an unperturbed eigenstate. Otherwise, you're not doing perturbation theory. So we can think of this as the large component and q as being the small one. Also, we can think of p psi as being the easy component because p psi is an unperturbed eigenvector. And the unperturbed system is solved. We know that. So we know what the unperturbed eigenvectors are. So p psi, whatever it is, lies inside that eigenspace, and we've got a pretty good handle on what it is. Whereas the orthogonal part is going to be the hard part of this analysis, finding the q psi part. Okay. Now, we need to develop equations for p psi and q psi, and here's how we'll do this. Let's go back to the original formulation, h0 plus lambda h1, which is the full Hamiltonian, acting on the exact eigenstate psi is equal to the exact energy E times the exact eigenstate psi. Let's just rearrange this slightly by bringing one term over the other side. And we're going to write this way as E minus h0 acting on psi is equal to lambda h1 times psi. So this is rigorously equivalent to the original Schrodinger equation. It's just a rearrangement. What we'd like to do with this equation is to divide by the operator E minus h0. It turns out it's convenient to do that. if we wanted to divide by E minus H0, we need the inverse operator. And there's a question of what the inverse operator even means. This is an example of a function of an operator. And way back in the very first lecture, I talked about functions of operators. And so whenever this question arises, what do you mean by a function of an operator? Refer back to that. If you do, what you find is what this means is that it's a sum over the eigenstates of H0. That's to say, it's sum over all k and all alpha, the outer product of k alpha, divided by the denominator, which is E minus, instead of H0, replace it by the eigenvalue epsilon sub k of the projector, which is in the numerator. So this is just what we mean by this 1 over E minus H0. Now, however, there's a problem with this operator, and that has to do with the terms in this sum for which k is equal to n. Let me put a question mark for those terms, k equals n terms. The problem is that since we're doing perturbation theory, the exact energy E is close to epsilon sub n, the unperturbed energy. And so when k is equal to n, that's epsilon n also. And the result is the denominator is small. It's small for the terms here, which are connected with the unperturbed eigenspace. Moreover, if we let lambda go to 0, then we just saw that the exact energy E approaches epsilon sub n. And so for those terms, that denominator goes to 0. And then the thing isn't even defined. So we've got some troubles with the k equals n terms. They have smaller vanishing denominators. And we're going to fix this by introducing a new operator, which I'll call R, which is exactly the same operator, except we suppress the terms which have the small denominator. So we sum on all k except n and alpha. Otherwise, the expression looks the same, k alpha outer product divided by E minus epsilon sub k. And this is R stands for resolvent, which is what this operator is usually called. It's related to the Green's functions, which occur in scattering theory, which we'll learn more about next semester. So now what I'd like to do is to tell you some things about this resolvent operator, because it turns out it gives us what we want. So in the first place, if I take the resolvent operator and I multiply by the projector P on either side, the answer is 0, because the projector P up here is projecting onto the states inside the unperturbed eigenspace, whereas the R is excluding those vectors, and so it's going to kill each of these k alphas if you apply P to it. On the other hand, if I apply Q to R, which is it's RQ in the other direction, applying either Q from the right or to the left, what Q does is it just reproduces each of these k alphas. It doesn't change them. So doing it either on the right or the left is going to reproduce and just reproduce R all over and just give you R again. All right. So what do these formulas mean? Well, they mean this. Let me go back to my diagram here in this space here. So the operator Q is the projector onto Hn perp, and it vanishes on Hn. What that means is it's really the identity operator on this Hn perp subspace, and it's 0 on Hn. Now, what about this this PR operator here? What this operator here, PRP equals 0, tells us that the R operator also vanishes on the unperturbed eigenspace. So both R and Q really live on this perpendicular space. That's the idea. Now here's another identity that R satisfies. If I take R and multiply it by E minus H0, or if I multiply in the other direction, E minus H0 times R, it won't matter. If I look at my expression for R, you'll see what happens. R is sort of a modified version of the inverse of E minus H0. Applying E minus H0 to this expression here, either from the right or from the left, is going to act on these k alpha terms and bring out E minus epsilon sub k, which is going to cancel the denominator. So these products here is the same thing as that sum for R, but without the denominator. So it's a sum on k naught equals to n, sum on alpha of k alpha outer product. But that in fact is the same thing as the Q operator. So what this tells you is since Q is the identity on the orthogonal space, it means that R is the inverse of E minus H0 on the orthogonal space, but it's 0 on the original unperturbed eigenspace. All right. Okay, so those are the principal properties of R. Now let's go back to our Schrodinger equation in the form of this E minus H0 psi is equal to lambda H1. And let's multiply both sides by R. If we do, then using this expression here, R times E minus H0 equals Q, then here's what we get is, can I bring this up a little bit? So I want to, I'm sorry, I keep moving this around. Let me try to hold it steady so you can see. I want to take this equation here and multiply by R on both sides. On the left-hand side, it's going to give me Q. Okay, and so what I get is Q psi is equal to lambda times RH1 psi, which is an interesting result because Q psi, remember, is the hard part, the small hard part. If we could find that, we'd have a long way towards solving the whole problem. In fact, let's take the easy part, P psi, and add it to both sides. And if we do on the left-hand side, you get the total psi is equal to P psi plus lambda R H1 psi. And let me box this because this is a useful result. This is really nothing but a rearrangement of the original Schrodinger equation, but it's in a useful form because the first term you see is the large easy part of the exact energy eigenstate, and the rest of this is the Q psi part, which is now written out in terms of lambda R H1 in the full solution psi. This is not a solution of the problem, but it's getting there because we've got the first part split off, the easy part split off. All right. Now, there are various ways of solving this equation approximately. One of them involves the method of successive approximations. That would be where you take the left-hand side and you substitute it into the small term on the right-hand side. If you do, you get another exact equation, which is more complicated, but starts to look like a power series. You can get the same results by rearranging things and dividing by an operator. I'll show you now how that works. Let's bring this lambda term over to the other side. And so we have 1 minus lambda R H1, that's the operator acting on psi, is equal to P psi. And then dividing by this operator, then I get psi then is equal to 1 minus lambda R H1 inverse applied to psi. 1 is the identity operator. Lambda is, we think of lambda itself is not small. It goes between 0 and 1, so 1 is not small. But the H1 is small, and the lambda serves a role of reminding us that the H1 is small. So if we think of this lambda RH1 term as a small correction, we can expand this effectively in a Taylor series and operators. And what we get is that psi is equal to, oh, this should have been
Sure.
psi right there. Yes, question.
That was it. Never mind.
Good, thank you. You would have caught my error. P psi there. So remember that P psi is the easy part. So just expanding the series out, what we get is P psi for the first term. Then we get plus lambda RH1 times P psi. Then we get plus lambda squared RH1 times RH1 times P psi, and so on. You can carry the series out obviously forever. And let me box this because this is a basic power. And in fact, let me write it out explicitly as in summation form. This is a sum from index R equals 0 to infinity of lambda to the R, capital R H1 raised to the power R times P psi. To write it out explicitly, this is the basic series out of which all of perturbation theory is, all bound state perturbation theory can be constructed. All right. So that's basically the derivation of the fundamental power series that we use for deriving all the results in perturbation theory. And from here on out, now what I do is I apply this to the various cases. So let me pause here and ask if there's any questions about this. I realize this is a little hard to follow, and some of the steps I try to motivate them as best I can, but this is what comes out.
Do cases ever come up in practice where that operator 1 minus lambda RH1 is not invertible?
Yeah, so there's a question of the invertibility of that.
Yeah.
Actually, they come up all the time. In fact, you'll find in quantum perturbation theory that typically the perturbation series are not convergent. Rather, they are asymptotic series. There's a whole, believe me, an amazing universe of asymptotic series and what they mean in the correction terms and so on. The ones that are beyond all orders of powers and so on.
Right.
So no, they in general they don't converge. In a little while, we'll talk about the Stark effect. And in the case of the Stark effect, you can see why it doesn't converge. It misses tunneling. You can go on grinding out higher order powers of perturbation theory forever, and you'll never see the tunneling. Different techniques are needed to get the tunneling. This is actually it raises a fundamental question in quantum field theory, it first appeared in quantum electrodynamics, but elsewhere as well. Because all calculations that people do, virtually all of them in quantum field theory are perturbative. They're based on power series expansions and perturbation theory. And it's known that those perturbation series don't converge. This was pointed out by Freeman Dyson back in the 1950s for quantum electrodynamics. So people are proud of the fact that you can carry it out to 8th order or something using a lot of computer algebra and so on, and get results that agree with experiments to 10 or 12 significant digits and whatever. That works. That's true. There's no doubt about it. But mathematically, what are you doing? There's no hope of getting an actual number out. What you're doing is you're getting a sequence which will get better for a while and then it'll get worse. So what is the meaning of the actual number? Does the theory even have an actual number that comes out? These are fundamental questions, and obviously engage mathematical physicists in connection with quantum field theory. But as a practical matter, if we carry it out to 1st or 2nd order, there's a whole host, or not too far, there's a whole host of problems that are solvable by perturbation theory. They give us good answers, in other words. All right.
Then actually a follow up on that, then how do we know in general that like what you just mentioned, that it will converge for the first some number of orders and then it will stop converging, or it'll stop agreeing with experiments? So then how do we know, why does it even agree with experiment to some number of orders in the first place?
Well, there are plenty of mathematical examples of divergent series that work well for a while. I mean, you start adding terms and they give you a good approximation, then it gets better, and then it gets better, and it gets better, and you carry it at a certain point, and then it starts to get worse again. So there's a minimum, where things get your maximum accuracy, and after that it just blows up and goes to pot. So this is not unique to quantum mechanics. I mean, if you just take Stirling's approximation and get those terms, Stirling's approximation is an asymptotic expansion. So why that's so, if you look at the derivation of Stirling's approximation, you can see why that's so. So, I mean, there's mathematical examples of divergent series where one understands this rather well. But what it means is you cannot use Stirling's approximation and the asymptotic series to calculate in factorial to an arbitrary precision. Precision might be pretty good for n equals 10, or whatever number you're interested in. In fact, it's remarkably good. But you can't add up, you can't get convergence in the sense of epsilons and deltas. There's going to be some minimum error that you can't get below.
Oh, I see.
So I sort of taught a course on asymptotics once. I mean, it was very, very interesting, very mind expanding. Okay, so all right, so anyway, so this is our basic series, and we'll use it quite a lot. Actually, written here in 2 different versions. The first application is to non-degenerate perturbation theory. Non-degenerate, if I can spell it. So non-degenerate perturbation theory means the case in which the energy eigenvalue n, so that what we called n alpha with alpha and extra index to resolve degeneracies, we'll just replace it by n since the alpha index is not needed. I'll retain the alpha index on the other states because it might be that they're still degenerate. We want to just take one that's non-degenerate. This means that the projector P is now equal to just n outer product like that. Okay. Now then, this also means that the P psi, remember P psi is a projection of the exact solution onto the unperturbed eigenstate, the unperturbed eigenspace. In general, that's what it is. But in the non-degenerate case, the unperturbed eigenspace is just one-dimensional and it's spanned by n. So therefore, P psi must be proportional to n. with some constant C. Now, what is C? Well, C depends on the normalization in phase for psi. We didn't say what that was, and you can choose it to be anything. So let's choose normalization in phase of psi to make C equals to 1. We can do that. If we do this, then of course what we get is P psi is equal to N. And this is the most convenient normalization for perturbation theory, for non-degenerate perturbation theory. However, it does not mean that psi is normalized in the usual sense that we do in quantum mechanics. You can see this from this diagram here. It means that P psi is normalized. In fact, it's equal to N in that case, but there's still the Q psi. So this means that the total psi that we're going to get out from this formalism is not going to be normalized. Don't worry about that when we're all done. If you want to, you can normalize it. But anyway, just a remark on it here. This just makes the algebra simpler if we do this. So let's do that. Anyway, if P psi is equal to N, then I can substitute it into my famous series up here, and all these P psi factors just become equal to N. So let me write that out. Write that out what we get if we do that. So now the series now looks like this, is that psi is equal to N plus lambda RH1 applied to N plus lambda squared RH1 applied to N, etc. like this. This is the series. All right. Now then, what we really like to get out of this series is still not a solution for psi. It almost looks like it is, but it really isn't. The reason is that these resolvent operators R contain the energy eigenvalue in the denominator. Besides, we need to get not only the eigenstates, but also the eigenvalues. So let's try to extract both the eigenstates and explicit formulas for the, let's try to get the eigenvalues and explicit formulas for the eigenstates out of this series. As far as the eigenvalues are concerned, what we do is we will take the scalar product of let's see, as far as the eigenvalues are concerned, let's go back to E minus H0 acting on psi is equal to lambda H1 psi. Let's go back to that. That's the original Schrodinger equation. Then let's multiply both sides by ket n like this. On the left-hand side, we get n on the left, E minus H0 in the middle, psi on the right. That's scalar product. The E minus H0 we're allowed to act on the n. E is a C number, so it just comes out. The H0 acts on n and gives me epsilon n. That's the unperturbed eigenvalue. What's left over is n scalar product with psi. Now, I didn't say that a minute ago, but this phase convention here tells me that n, if I sandwich both sides with n here, what I get is n p psi is equal to 1. But p acting on n just gives me n, so that's the same thing as n psi. So this phase convention gives me n scalar product with psi is equal to 1. And so this thing just becomes n equal to E minus epsilon n on this left-hand side. And on the right-hand side, it's just the right-hand side multiplied by bra n. So that becomes lambda times n h1 psi, like so. Okay. Okay, so on the left, I've got E minus epsilon n. That's the energy shift due to the perturbation. Good, we'd like to know that. On the right-hand side, I've got this matrix element, but there's a side, I don't know what that is. So let's take our magical series and let's plug that in there like that. And if I do, then here's what I get is I get E, and I'll bring the E in over the other side. I get total E is equal to epsilon n. And then we get plus lambda h1, lambda bra n h1 multiplied times this entire series. Well, the first term has just got an n in it. The second term has got that, so you get plus lambda squared n r h1. Sorry, it's like this. It's h1 r h1 n. The next term is lambda cubed times n h1 r h1 r h1 n. You see iterated factors here of plus dot dot dot. You get a series like that. All right. Now, again, this looks like, it almost looks like we've got a solution for the energy eigenvalue out to all orders. It isn't quite as simple as that. And the reason is that that the energy is actually contained in R. The definition of R involved the energy in the denominator. Here it is right here. Okay. So for example, if I write out this second order term like this explicitly, what is this equal to? It's a sum on k not equals to n, because we excluded those terms from R, and a sum on alpha. And then we have n scalar product n h, you can see n scalar product h1. And then the R's got the projectors, the outer product k alpha. That comes from the R part. And then you've got an h1, and then you've got n like this. And then this is divided by E minus epsilon sub k. That's plugging in the definition of R for that second term. For the third term, you got 2 copies of R. So the E appears both on the left-hand side and on the right-hand side. However, on the right-hand side, the E appears only in second order. So this is we know E to 0th order, that's the unperturbed energy. We know its first correction, there it is. We can take these 2 terms, or just the epsilon n is good enough here at second order, and plug into there, and we still get the result valid to second order. So in other words, this E can be replaced valid through second order by epsilon sub n. Now, if we do this, then we can summarize the results by writing it this way: is that the energy shift in non-degenerate theory at first order, let me write it as delta E sub n with a superscript 1 giving the order of perturbation theory. That's just this first term here. That's equal to, and I'll suppress the lambda now, I'll set lambda equals to 1. We get n h1n, like so. Then delta E at second order perturbation theory n is equal to the sum on intermediate states k not equal to n and alpha, like this, of n h1 k alpha outer product here, and then an h1 and an n divided by epsilon n minus epsilon sub k. And these are the 2 main results, most useful results in non-degenerate perturbation theory for the energy shift. As far as the wave function is concerned, we can go back up here to our formula here. Here's the full series for the wave function. The 0th order term, of course, is the unperturbed wave function n. Here's the first correction. This R again has an exact energy in it as in the denominator, but we can replace it by the epsilon n valid. If you want to stop at that order, we can just replace it by epsilon n. And if we do this, then we get the expression for the wave function psi, and that's equal to n plus, again, the same sum on intermediate states, k not equal to n, sum on alpha. We get k alpha like this, k alpha, h1, n, and then the same energy denominator, epsilon n minus epsilon sub k. And this is valid out to first order. So these are the main results which we have in the non-degenerate perturbation theory.
Isn't alpha always going? Aren't we going to have not more than 1 alpha if it's non-degenerate?
When I say non-degenerate perturbation theory, I mean that the state whose perturbations we're looking at is non-degenerate. That's the state I'm calling n. So that's why earlier here I replaced the n alpha just by n. But as far as the other states are concerned, we're allowing them to remain degenerate because in practice, that's what you have.
Okay, I see.
Well, I mean, I'm trying to be practical here by doing that.
Yeah.
So the other states, by the way, I've been calling these states k not equals to n. I've been calling them intermediate states. This is language which is used in perturbation theory. Notice that these states you're summing over are excluding states from the unperturbed eigenspace. That's all what we did with that R operator, leaving those dangerous denominators out. But what that means is that this first correction term to the wave function is actually orthogonal to n. It's orthogonal to the unperturbed state. In fact, you can see this is an approximation to that Q psi part. This is the P psi, the way we've been doing it right there. And this is the approximation of the Q psi. You can indeed see that it's orthogonal. Also, as I commented earlier, the normalization convention we were using is one that does not make psi squared equal to 1. But it almost does, because n squared is 1, and n product into the first correction is 1. So actually the correction is only going to come from second order, where I square this, this first order term squared is going to give me second order correction of the normalization. A lot of applications you wouldn't care about that, and this is actually okay the way it is. All right, anyway, that's a summary then of a non-degenerate perturbation theory. Are there any other questions about that before I go on to the degenerate case? All right. These are formulas you should have derived in your undergraduate courses. And in fact, for the most part, that's all we're going to use in this course too. But there are some, in the homework problems, you'll see some variations on this. All right. So let's move on to degenerate perturbation theory. For degenerate perturbation theory, we go back, if I can find it here, we go back to the, here it is. This is the central series that we use in all versions of perturbation theory. Here's where I drew the line and started working in the non-degenerate case. So since we're done with that, let me fold it out of the way. And let's start talking about the degenerate case. So in the degenerate case, P psi lies in the unperturbed eigenspace. Therefore, P psi must be representable as a linear combination of the vectors in beta with coefficients I'll call C beta. Whatever it is, there must be an expansion like that. So that's something that I can plug into all these P psis that I see up here on this side, this right-hand side here. Now, let's see. Here's something else we can do. Let's see, let me make sure I've got this right. Yeah, so before I leave this equation, let me do this. Let's take N alpha scalar product with, let's take this equation and multiply on the left by one of the unperturbed eigenstates N alpha. This I value in two ways. First of all, the P acting to the left on this doesn't do anything to it because that's an unperturbed state. So that's just N alpha times psi. Whereas on the right-hand side, it picks out the term alpha equals beta. So that's equal to C alpha. So that gives us a useful result, which is that C alpha is equal to the scalar product N alpha with psi. Let me circle that because we'll need it later. All right. Now then, let's go back to our original Schrodinger equation, which we wrote in this form E minus H0 acting on psi is equal to lambda H1 acting on psi. I'm going to use this equation to get the energy eigenvalues. So let's see, how we're going to do this is to take this equation and multiply on the left by bra N alpha, like so. So on the left-hand side, we get N alpha. This is following what I did in the non-degenerate case, but now there's an extra index around. So we have E minus H0 psi like this. We let the E minus H0 act to the left. The E is the number and comes out. The H0 brings out the unperturbed energy, which is epsilon N. What's left over is N alpha times psi. But N alpha times psi, we just decided is C alpha. So I get E minus epsilon N times C alpha. All right. But that's equal to N alpha multiplying the right-hand side. So that's lambda times N alpha H1 multiplying psi, which is this series up here. All right. Now this series up here, let's look what we've got. Can you see it? Yeah, here's the series. It's all full of P psis here. The P psi we expanded in terms of unperturbed eigenstates. So let me rewrite this in a different way then. So what we've got is that psi is equal to, I'll take all these factors of P psi and I'll put them out to the right. So it's equal to 1 plus lambda RH1 plus lambda squared RH1, etc. Multiplying onto P psi, which is the sum on beta of N beta times C beta, like so. And then I want to put that psi into there. So let's gather that together and do it. And what we have is E minus epsilon N times C alpha. Let me take this sum beta and bring it over to the left-hand side like this, which I can do. And what we get then is this is equal to the sum on beta. And I get N alpha H1 multiplying times this series. So there's this collected here. We get N alpha H1 times the 1 times the N beta. Then we get N alpha times from this term here, N alpha times H1 times RH1 times N beta. This is a lambda here, plus dot, 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 and this whole thing is then multiplying onto C beta coming from there. All right, let me box that. Because this is in effect the energy equation for the non-degenerate theory. Now then, what does this say? What you can see here is that there is a matrix in here in indices alpha and beta. The alpha and beta run from 1 up to the, let's call it G sub n, which is the order of degeneracy of the unperturbed eigenspace. So that's what this is indexing. And what you've got here is it's matrix elements in alpha and in beta inside the unperturbed eigenspace of operators that get progressively more and more complicated at higher order. So this is a matrix in alpha and beta, and it's multiplying the coefficient C beta. And what it gives us is what's effectively is an eigenvalue of this matrix times the eigenvector C alpha. So what this shows you is that the C alphas, which are the expansion coefficients of P psi in the unperturbed eigenbasis inside the non-degenerate, inside the unperturbed eigenspace, are the eigenvectors of this matrix. And you can see the eigenvalues are the energy shifts away from the unperturbed eigenvalue epsilon sub n. Even though I'm right in the thick of it and right in the middle of it, I think I'm going to stop there because I'm out of time. And so we'll continue this next time. Are there any questions about this so far? All right, if no questions, then that finishes us for tonight. As soon as we're almost through perturbation theory, there's only 5 minutes left to say about it. And when we're done with that, we'll start doing some applications. In fact, we're going to do applications for the rest of the semester. All the formalism we built up in the last several weeks, we're going to get to apply it. All right, if there's no more questions, I'm going to stop the screen share. And one last call for questions before I stop recording. Okay, here we go.